All right. Everybody get a chance to draw this? All right. What example is this? Was it 9? Example 9, part C. Okay, did we all get a chance to draw it? Yeah? Okay. What forces are acting on number 1? Gravity. Which way is gravity pull, Kim? Down. So you have the force of gravity down. Okay. What else? I'm going to draw that one just a little shorter. I want to make them all comparative in length. What else?
2 and 3.
Not 2 and 3. Okay, not 2 and 3 though. 3 does not apply a force to 1. 2 applies a force to 1, right? Okay. So 2 will apply a force to 1. So this is the force of 2 on 1. Right? Force of 2 on 1. I appreciate the effort though, Kim. I'll make that one just a little bit longer. Anything else? Any other forces? So object 1 is accelerating downward.
There's tension.
There's tension. Which way does that pull? Up. Now, how does tension compare to these two? Should be equal. So I'll apologize for this right away. So that force, I don't have enough room and I don't feel like writing my wall today. All right. That force should be equal to these two in length. Right? Man, that's terrible. It's not even straight. Yes.
Do we have to make the object 2?
Yeah, because I'll show you in a second. Okay? Let's go on to 3. What forces are acting on 3?
Gravity.
Gravity. Which way does gravity pull? Sideways. Okay. Now 3 is bigger than 1, so the force of gravity is going to be 3 times longer, right? What else is acting on 3? We have force of gravity, Sergio. What else is acting on 3?
I was just thinking about how force gravity is bigger.
You hear what you say? 2, right? 2 pulls on this rope, which pulls on 3, doesn't it? So 2 is applying a tension to 3, but so we don't get confused, we're going to call it the force of 2. The force of 2 on 3. So 2 is applying a force to 1 and to 3. Kind of interesting. 2 pulls 1 down and pulls 3 up.
Wait, did you say that again?
2 pulls 1 down, but pulls 3 up. Does that make sense? Okay. What about number 2? Gravity, which way? Downward, because someone said sideways last time. Okay. So gravity pulls 2 down. Now it's not as long as 3, but not as short as 1, right? That looks like it's just as short as 1. There we go. Okay. So force of gravity down. What else?
1 and 3.
Okay. So someone said 3 down. So 3 pulls down on 2. Right? How does it compare to the length of this? Same. So it's the force of 3 on 2. And then someone over here said something about the other one. 1 on 2. Which way does 1 pull? Up. Now, how does 1 compare to the length of these two? Should be equal. Okay. That's the force of 1 on 2, right? And all these are vectors. Sorry, I didn't draw my arrows. Okay, just kick my water. So, any questions? Any questions? Yes, Lynn. Yep, because in the problem it said this is 1 kilogram, this is 2 kilograms, and this is 3 kilograms. Okay, so they have different masses, which means they have different force of gravity. Okay, anyone else?
Wait, so
Michael?
Can you go over number 1, please?
Number 1 again? Okay. We have gravity pulling down, right? Just like gravity pulling the marker. We have gravity pulling down, right?
Yeah.
And to support that gravity, we have tension going up, right? But also number 2 pulls down on number 1. Because number 2 is hooked to number 1.
Oh.
Okay, does that make sense?
Yeah.
Okay, it's like I have the mast, and the hook on top is hooked to the ring stand. Okay? And then there's that little hook on the bottom of the mast sometimes. The hook on the bottom has another mast hook to it. Okay, does that make sense?
Yeah.
Okay. All right, anyone else? Sergio, you have something to say?
Yeah, so the force tension for 2 is equal to 1.
What do you mean?
Isn't the force pulling up or whatever, force 2 is equal to 1. The tension.
So,
force 1.
Are you saying this one?
Yeah.
Force of 2 on 1?
Yeah.
Or sorry, force of 1 on 2?
Is equal to force tension in 1.
Which one? Top one or bottom one?
Top.
No.
Top row. It's not.
No. It's not. But it is equal to force over here. Which one? Okay, let's figure out the new third law of pairs. Which one's our third law of pairs? Victor?
2 and 1 and 1 and 2.
Okay, so 2 on 1 and 1 on 2. These are our third law of pair, aren't they? You want to draw like a dotted line that connects them? And they're our third law of pairs.
3, 2, 2, 3.
Good. That's why we label them this way, right? So we can identify our third law of pairs. Right? So those ones are our third law of pairs, aren't they? Right? Now, which rope does 2 on 1 and 1 on 2 occur in? I'll label my ropes. We'll call this rope A, rope B, rope C. Where does 2 on 1 and 1 on 2 occur? Which rope? B. Where does 3 on 2 and 2 on 3 occur? Rope C, right? So 2 on 1 and 1 on 2 happens here, right? Because when you pull on a rope, when you pull on one end, right, the same force is applied to the other end. That's how a rope works, isn't it? Right? When I'm reeling in a fish on a fishing line, the fish pulls with some force away from me. That's pulled. I feel that same force on the fishing rod, right? I pull on my end of the fishing line with a fishing rod. The fish feels that same force. Does that make sense? So the tension in each rope is equal on both ends, and that's what this kind of shows me right here. Okay? And the reason why it's equal is Newton's third law. Okay. Newton's third law says the force tension on both ends is equal. Does that make sense? Okay. Any questions? Okay. Now the second part of this said, which rope, which force, which tension is the greatest? Which tension is the greatest? A, B, or C? Let me throw out some possible answers. A student might say the one in C is the greatest because that's a 3 kilogram mass. Okay? Someone might say C is the greatest because it's a 3 kilogram mass. Are they right? No, why not?
That's just 3 kilogram mass, but it's at 0.8, it'll be all added up together, right?
Why is point A holding all of them?
Because it's the top row, and that's what's holding up 1, 2, and 3.
So this one, so A holds up 1, 2, and 3?
Well, it holds up 1, which holds 2, which holds 3, and like, what did you add them up together?
Okay. Yes, Emmett. Sure. Okay. So A holds up 1, 2, and 3, right? Okay. So A holds up 1, right? But 1 is also holding up 2, which is also holding up 3. So 3 applies a force on 2, pulling it down, right? 2 applies a force on 1, pulling it down. But that force from 3 is also pulling on 1 through 2. Does that make sense?
Yeah.
So this force up here, this rope up here will have the most tension because it's not just supporting a 1 kilogram mass, it's also supporting a 2 kilogram and a 3 kilogram.
So it'd be 6.
So that one's supporting a 6 kilogram mass. So this rope at A feels like it's supporting how many kilograms? 6. So if I asked you just for the tension of rope A and nothing else, you could just do 6 times 9.8 and figure out your answer. Okay. So up here we know that the force tension up here equals force gravity plus F 2, 1, right? Does that make sense? Yeah. And we know F of 1, 2 equals force gravity plus 3, 2. Right? And we know 3 comma 2, or 2 comma 3 equals force gravity. Right? Right, guys? Now this force gravity right here, this is 3G, isn't it? 3 times 9.8. Right? So then I can plug that in right here and have F of 1 comma 2 equals this force gravity. Is it 3G or 2G? 2G plus 3G. Does that make sense? Right? So this tension is only 3 times 9.8. This tension is going to be not 3, not 2, but 5 times 9.8, right? Does that make sense? Okay. And this tension is going to be, this is, how many G's? 1G, because it's the mass 1, right? Plus 2 comma 1, which is 2G plus 3G. So this tension up here is going to be 6G, 6 times 9.8. Does that make sense, guys?
A little bit.
Okay.
Did you just convert 2 and 3 to the FGs?
What do you mean?
Because you don't leave it as 3 F3 2.
Right. This FG right here is just for the third mass, the 3 kilogram mass. This FG is for the,
3 and 2.
nope, the 2 kilogram mass. This right here is that force. So that's the 3 kilogram mass. Okay? So this 3 kilograms gets plugged in, or yeah, 3 kilogram mass gets plugged in here, right? This is 2 kilogram mass times gravity. Okay? Does that make sense?
Yeah.
Okay. So this right here, guys, proves that the top string has the largest tension. And long story short, that top string only feels like it's holding a 6 kilogram mass. So to that top string, if that top string could see, it would think it's doing this.
If only ropes could think.
Only ropes could think and see, right? That's what the top one would feel. All right?
What if the ropes are like rubber bands?
Then they would stretch. And that is a different situation, which we'll discuss later on this year. Okay? Trying to get me off topic. No, that's a good question. All right, any other questions?
Save.